Okay, here's GPLA, which is short for General Purpose Ladder Analysis. And we can open up that 20 meter double tune circuit and look at its frequency response. And there it is. We can also review the circuit with this essentially ASCII text listing so that we can literally go back in and change component parameters, either values or say the Q of the inductors, to do what-if experiments on how the circuit would behave with different values of components. So what I'm going to do here is drop back and change the scale here on the vertical so we can zoom in, and let's come in a little bit tighter. Let's say 12 megahertz on the low end, megahertz steps, and 16 megahertz for the top sweep. You can notice that there's a little bit of tilt in the passband, and that's nothing unusual. Note the double humped response of the return loss. In this case, in the band, we're doing pretty good, but out, here, not very far out beyond the band edges in terms of 3 dB down, we're not all that doing all that well on return loss. So this is a motivation sometimes for widening the filter a little bit to push these band edge return losses out so that we have a better return loss in the pass band. Now in this case, we have a number of choices of investigating what-ifs, and a key one that's significant for this case is if we go in and modify the series coupling cap. In this case it's element number 5. So we can come down here for element number 5 and bring that up and just set it to, say, 4 picofarads if we didn't have enough coupling. And you can see that the double humped response of the return loss has now narrowed in on itself. And if we even make it worse, go down to 3 picofarads, you can see the fact that the flatness in the passband has essentially been eliminated, and the insertion loss is increasing quite a bit. And so if you have a double tune circuit and you only see one return loss response in terms of a dip, then you know that the coupling has been goofed. Now, at the other extreme, if we come out here to, say, 5 picofarads, it's still looking pretty good flatness. So you can see from that maybe a 5% variance on the capacitance isn't going to be much, but let's come out and look at what 10 picofarads would do. And this is classic of overcoupling, and we'll accentuate it by going to, say, 20 picofarads. And here's where some people historically were deceived on some of the filters they would make, where they would see a response like this one out here, where we can place a cursor and find out what that is. And the cursor is at 14.44 megahertz. Well, they would see this response and then tune the resonators so that it went back down into the passband, and they only had one response here, but they had another peaked response down here at 12.57 megahertz that they wouldn't know about if they hadn't swept, as Wes would always say, DC to light. And so you need to do a pretty good sweep on filters like this to make sure you've captured everything. And this is just the nature of them. But also, if you don't have software available and don't feel like doing the math right away, you can put an air variable capacitor, or just variable capacitor in general, as a coupling element if you have got a good idea ahead of time of approximately what the value ought to be. And you can tune it around while you sweep through the response until you get a response that you like. And the beauty of it is that if you're willing to live with a little bit of a passband ripple, maybe on the order of a half a dB, you get inherit quite a bit of flexibility on widening or narrowing the bandwidth of the filter if you want to pull the 3 dB down responses in tighter or spread them out a little bit. And sometimes this is relevant when you might have wound inductors on toroids where you couldn't measure them, and you wound up with toroids that were off in value, which then meant that the tuning caps were tuned differently, but also that maybe your end section capacitors were compromised. Now in this case, let's go back and look at what the end section sensitivity is. So we can go to capacitor number 2, and let's make that 30 picofarads and see what happens. Yeah, not much difference. But we need to go back and address the other side. So that's item number 8, or number 8. And so now our double hump response in the middle is still pretty well behaved. And you can see that the passband response in terms of ripple hasn't changed all that much. And let's even go back for more standard value capacitor on 8. Number 8 goes to 33, and number 2 goes to 33. And there we've still got a very nice response and very good symmetry here. So we went from 29.7 to 33, and things were still looking quite nice. So this allows us to do what-if experiments in terms of junk box capacitors, or capacitors that we have on hand that might not fit exactly what the original calculations indicated. And this is one of the many features of GPLA that makes it very nice for amateur homebrew experimenting. So that's essentially the nature of GPLA and how it would be used with filters.